So we are going to start Unit 2 today, Lesson 1 of Unit 2 of Algebra 2. And this unit is a unit on polynomials. So a polynomial, as it says here, is any mathematical expression that has more than one term. Okay, the prefix poly means many. Okay, so a polynomial is one with many terms. We have binomials, trinomials, quadrinomials, etc., etc. Polynomials are used to model different everyday mathematical situations. One of the ones that we're going to look at today in the examples is modeling the volume of an open top box. All right, so this is a box in which you take a piece of paper or cardboard and you cut out a square of the same size from each of the four corners. And when you do that, you end up with this polynomial. Now, that will obviously depend on the length and the width of the original piece of cardboard or paper. We're also going to talk about something called the domain, and we'll get to that in a little bit. But to make a little more sense of these lesson notes, we're going to take a look at the examples here. So let's go ahead and do that. So imagine constructing an open top box from a standard 8.5-inch by 11-inch piece of paper by cutting out the same size square from each corner and then folding up the sides. What would the dimensions, length, width, and height of the box be? Fill in the appropriate columns of the table. Draw a diagram if need be. So a standard piece of paper is 8.5 inches length by 11 inches width. And notice I put that in here. I drew a rectangle. Obviously, a piece of paper is rectangular. So the length is 8.5. The width is 11 inches. Okay. And what they're saying is we would make a box out of this by cutting a square, an X by X, a square from each side of the piece of paper, from each corner of the piece of paper. So that's what I drew in red here. And essentially what would happen is you would fold it up and then you would have an open top box. Okay. So what this table is saying is if that square that I cut from each corner is a 1/2 inch by a 1/2 inch, what would the length be, the width be, so on and so forth? What if the square is 1 inch by 1 inch? So these X's are ones. What would the length, width, and the height be? Okay. How about 1.5? What if it's 1.5 inches by 1.5 inches? So on and so forth. Okay. So if I, for example, look at the length right here, okay. Look at the length we know is 8.5 inches. Okay. What if I cut off a 1/2 inch from each end? Like if I cut off a 1/2 inch square from each end, that's going to take off 8.5. That's going to take off a 1/2 an inch here and a 1/2 an inch here. That's going to bring me down to a length of 7.5 inches. Okay. For the width, if I take off an inch, a 1/2 inch here and a 1/2 inch here, that's going to bring me down to 10 inches. Okay. And then think about it. If I fold it up to create a box, that height is simply going to be a 1/2 an inch. Okay. What if I make that square 1 inch by 1 inch? So what if I take 1 inch off from each end here? What if I take off 1 inch off? That's going to take off 1 inch on the right and 1 inch on the left. So that's going to bring me down to 6.5 inches. Okay. That's going to bring me down to 6.5 inches. For the width, if I take off 1 inch up here and 1 inch down here, and that means I'm going to take off 2 inches total. That's going to bring my width down to 9 inches. And now my height is going to be 1 inch. Okay. Hopefully you're starting to see a pattern here. So if I make the square length, the square side length 1.5 inches, so that means I take off 1.5 inches here and 1.5 inches here, that's going to bring me down to 5.5 inches, because that's going to take 3 inches off the original 8.5 inch length. Okay, and on this side, it's going to be, again, if I take off 1.5 inches here and 1.5 inches here, that's going to bring me down 3 inches of width to a total of 8. And that will make my height 1.5 inches. Hopefully you're seeing a pattern here. This is going to go down by 1 each time. So this will be 4.5. This will be 3.5. This will be 2.5. And this will be 1.5. And this will be 7, 6, 5, and 4. And this will be 2, 2.5, 3, and 3.5. So I have my length, width, and height. That is the answer to number 1. Okay. Number 2, calculate the volume of each box. Fill in the last column of the table. Well, to do that, we're going to use this formula right here. Volume is length times width times height. So that's going to be 7.5 times 10 times a half is going to be 37.5. So you can just do this on a calculator here. So I'm going to do the same thing. So then we have 6.5 times 9 times 1. That's going to be, my calculator messed up here. It's going to be 58.5. Then we have 5.5 times 8 times 1.5. It's going to bring me up to 66. Okay, then we have 4.5 times 7 times 2. It's going to be 63. Then we have 3.5 times 6 times 2.5. That's going to be 52.5. And we have 2.5 times 5 times 3. It's going to bring me to 37.5. And then 1.5 times 4 times 3.5 is going to be 21. Okay, so I filled out the table, and you can see it looks like we reach a maximum somewhere in here. Okay, we don't know where, but we're going to figure that out in a moment. But I filled in that table. Okay, so this is number 1 and number 2 is filling out this table. Number 3, the volume in cubic inches of the open top box is a function of the side length x in inches of the square cutouts. Write an expression for v of x. Well, if we look at the lesson notes here, okay, you'll notice it says the volume of a box. We're going to use this template right here, where it says v of x. So notice, let me write this down here. So this is for number 3. It says v equals, or v of x equals, v of x equals length minus 2x times width minus 2x times x. Okay. So what we're going to do is we're going to fill in the length. Now, what did we say the original length was? The original length was 8.5 inches. So this is going to be 8.5 minus 2x. And the width, remember, is 11 minus 2x. Okay, so this right here, okay, this is an expression for the volume of the box when I have an original piece of paper of 8.5 by 11, meaning I can plug in, if I plug in, say, a 1/2 inch for X, okay, I should get a volume of 37.5. Okay. If I plug in 1 for X here, I should get a volume of 58.5, so on and so forth. But that is your expression. Okay. Number 4, use Desmos to create a graph of your equation. Use that to find a reasonable domain for this equation. So I'm going to take this right here, and I'm going to graph that on Desmos. Okay, so if I do that, so we have 8.5 minus 2x. We have 11 minus 2x. And then x. Notice we get kind of a zigzag type graph here. So what I'm going to do is I'm going to click on the wrench here, and I'm going to try to get a better view of the graph. I'm just going to kind of play around with the settings. Okay. So let's go. Let's see. 10. And then let's go from. Let's go. Oops. And then this one, I'm going to go from, say, let's go -20 to +30. No. All right. So I just kind of played around with the window setting, and I got a pretty good view of the graph here. Okay. So to find the reasonable domain, to answer that question, okay, we're going to go back to our lesson notes. Okay. So the reasonable domain is the set of all the input or X values that make sense in the context of the situation. Okay. So it's the set of all X values that would make sense in the context of the situation. In this case, the situation is making an open top box from a rectangular piece of paper. So to find reasonable domain, we're going to graph the function in Desmos. Okay. Step 2, we're going to find the 2 points that are x-intercepts and where the graph is positive between them. So I'm looking for 2 x-intercepts, meaning 2 points where the graph crosses the x-axis, where the graph is completely positive between them. So notice in this case, in this graph here, there are 3 x-intercepts. It crosses the x-axis at 3 points. So I'm looking for the 2 x-intercepts where it's completely positive between them. It can't be these 2 because the graph is negative between them. So it's got to be these 2. Notice the graph is completely positive between these 2. Okay. And graph is completely positive between those 2. So that right there, the reasonable domain is between those 2 points. So the reasonable domain, we would say, is between 0 and 4.25. So to answer the question, the reasonable domain is between 0 and 4.25. Okay. So again, how did I do this? I took the function that I had created, I graphed it on Desmos, and I looked for the 2 x-intercepts, the 2 points that are x-intercepts, and where the graph is completely positive between them. So that ended up being these 2 points here, between 0 and 4.25. If we take a quick look at your cooldown for today's lesson, as we wait for that to load, if you look at the cooldown, And this is taking a little longer to load than I would hope. Okay. So notice in this particular question, we are notice that the original piece of paper is going to be a different size, but we can still answer the question. So it's going to be basically the same thing you just did. Okay. The same thing you just did, except with a different sized piece of paper.